Well, hi everybody. We're going to have another really interesting look at the area of probability, and we're specifically looking at the topic of discrete probability distributions, and that's what we're going to cover today. And you'll find that most of it is already familiar to you. So just relax, sit back, and have a nice cup of tea ready, and let's go. Okay? Discrete random variables and probability distributions. Da-da-da-da. Here it comes, okay? So, that is a tree diagram with some discrete random variables annotated on the right-hand side, as you'll see how to do very shortly, okay? And you're a star. Of course you are. And you'll go far. So let's keep going. You've got your cup of tea? Pause me if you haven't, and I'll see you when you're back here when you've got your cup of tea ready. Okay? Right, now we've got a jar, and the jar has 4 white and 6 black balls in it. What are we going to do with those balls? Well, we're going to draw 3 balls in a row with replacement. In other words, we're going to put them back each time we draw. Okay? Right, and we need the sample space, and we also need the probabilities associated with each of those events in the sample space, okay? Now, let's draw a tree diagram. That's always the way to go with this. There's our first draw. White or black, yes. What are the probabilities? Well, there they are. You've got 4 out of 10 for white, 6 out of 10 for black, yes. Here comes the second draw. This is easy as, yes. Same probabilities because we're doing it with replacement. White or black, white or black. Third draw coming up, same thing, same probabilities. No problem. Now, let's have a look at what each of these little events are in our sample space. So I've just written them there for you in fast motion, but you get the idea. Everything from white, 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 down to black, 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 and in between. Okay? Now we'll look at the probabilities for each of those events. Now it's pretty easy because the probability of white is 0.4, and so that first instance was 0.4 times 0.4 times 0.4, which gets you 0.6064. Excuse me. Okay, and so on and so on and so on. The second one was a white, white, black, so that's 0.4 times 0.4 times 0.6, because the black's 0.6, gets you 0.096. Now listen, guys, be careful with these decimals. How I do these myself in my mind is, for that second case, I would multiply 4 times 4 times 6, and I would get 96, and then I would move the decimal point over to the left 3 spots, because each of those things that we're multiplying together has a decimal point 1 to the left, okay? So that's what you do. Each of them causes you to go left 1, so you're left 3 altogether after you get your answer of 96, okay? That's what you do. Now here comes the rest of them. Da-da-da-da, done in fast motion for you. Now, this is everything you've seen so far is absolutely stock standard. You've done all this stuff before, you've done it to death. You know how to do it. But we're leading up to something now which is different. So, first of all, you've got to verify that the total comes to 1, otherwise you're in a spot of bother, and you've got to go back and check. And I did check those, and yes, they do add up to 1, so I'm feeling good. Give myself a nice tick. Good. Now, I'm going to rub out some of that working up there to leave me space for the discrete random variable stuff, which is coming up. First of all, oh yes, the sample space, forgot that. The sample space is written there with that E for epsilon. That means the universal set, or everything that there is possible in this particular instance, this particular scenario of drawing the 3 balls out of the jar. So I've just written them there in the same order as that they appeared in my tree diagram, so that I didn't leave any out or mess it up, and that's it. That is your sample space, all right? Now, let's do the rubbing out now, and we're going to look at the new bit. This is the new bit now coming up. This is, we're going to call X, capital X, that's what they seem to call it all the time. capital X is our discrete random variable, and we're going to say let X be the number of white balls drawn. Now, this is the new bit. This is what we are interested in, okay? So, the number of white balls drawn. It's always a number, okay? A discrete number. So, let's have a look down the list of our white, 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 black, etc. in the tree diagram and see what the value of X would be in each of those instances, okay? Yes, X is a discrete random variable. That's the new bit we're doing in this chapter, okay? Right, here it comes. See all those purple annotations there of the value of X? Have a quick squeeze down there and see if you agree with me. Because X is the number of white balls drawn, okay? Yeah, that's right, okay? You see? Good. So, what's next? We want to know what is the probability that if a ball is drawn 3 times from a jar containing 4 white and 6 black balls with replacement, that a white ball will be drawn exactly once, okay? That is the situation when capital X is 1 in the table. So here's a table summarising exactly all those possible draws with their values of X. Okay, have a quick look, verify that you're satisfied that that's right. I think it is right. Yes, it looks right to me. Good. Now, what we're going to do is we're going to just copy what we got for the probabilities of those instances, which we got on the previous page, okay? So they're lined up with the values of X. That's pretty important, like that, okay? Now, the next thing we're going to do is when X was 1, that's what we're supposed to be working out, okay? There's 2 instances I've just spotted, and there's a third one when X was 1. So what would be the probability that X is 1? In other words, 1 white ball drawn. Well, guys, you know the answer. It's just the sum of those individual probabilities, because we could have a black, white, black, or a white, black, black, or a black, black, white. And the or means you add up the individual probabilities, okay? Whereas and/ors means you multiply them. So that comes to point 432 and Mr. Box. Thank you, Mr. Box. That is our answer, okay? That is our answer. All right, it's easy, isn't it? Now, just for your benefit, I'm going to show you the information of all the possible values of X summarised in a probability distribution table. Okay, a discrete probability distribution. Now, there is a nice little table which shows you 2 rows. The first row contains all the possible values of capital X, but I've written them as little x, meaning the specific actual values. They can be 0 or 1 or 2 or 3. The second row says the probability that capital X, meaning the number of white balls drawn, equals little x being the value, the specific value shown in the line above. Okay? Now we can just read them off from the probabilities we've got in our table there above. Okay? Now for X is 0, let's see. X is 0, there's only 1, isn't there? That's the very last entry in that blue table above. That's 0.216. When X is 1, that's different. There's how many? Oh, that's what we got above, didn't we? Yeah, that's what we got in the calculation above with the box around it. 0.432. Now let's look for X is 2. Looks like 3 instances, which add up to 0.288. And if X is 3, we've got 1 instance, the very first entry. Okay, and that gets us at 0.064. Now please add up to 1. It does. How excellent. Big tick for us. Now that is a discrete probability distribution shown in tabular form. Okay, that's it. That's what it is. Now the other thing to do is to show you a graph of it. There is a graph. Shown on the horizontal axis, we've got the specific values of X which can occur. You'll notice that the 0 value of X does not occur at the origin. We generally don't do that in these graphs of discrete probability distributions, because you're really only dealing with one value, one dot on the page for each of those values of x being 0, 1 or 2 or 3. And they can be hard to see, so you don't draw them right on the origin because you can miss them. You see what I mean? So that's how you do it, like that. You'll notice there's some dashes, vertical dashes, going from the x-axis up to the actual point, and that the points have coordinates shown to make them sort of more visible. You don't have to do those dashes if you don't want to, but you do want to make them a bit visible. The probability, of course, is on the vertical axis. The value of x, specific value of x, is on the horizontal axis. Now, they are discrete points. Yes, they are discrete points. So please do not join the points together. They are not to be joined. It's not a continuous curve. They're just discrete individual points, right? So don't join them. That would cause you to hemorrhage some marks. Okay? So that's the deal, guys. That is a discrete probability distribution. Let's do an example now, a different example. So we're going to do number of tails shown when a fair coin is tossed 3 times. No problem. In A, we've got to find the probability distribution of x and show that all the probabilities add up to 1. In B, we've got to find the probability that 1 or more heads shows. That's nasty because we're talking about tails, aren't we? Oh well, we'll fix it, don't worry. In C, we've got to find the probability that more than one head shows. Yeah, no problem. Let's do a tree diagram. There's the first coin, there's the second coin, there's the third coin. Good. Now let's just analyse what we've got here. Okay, head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. Okay, good. Now we're going to do the probabilities. Now it looks like each of those, if you think about it, of those triple combat events, single thing in every twig has a probability of 0.5. So because you've got 3 events there, it looks like every single one of them is going to have a combined probability of 0.125, which is 0.5 cubed. Okay, so let's just put that in. Good, good, good. Now, okay, we've got to worry about x now. Right, yes, it's the number of tails that we get. Okay, so there's x for the first one, x for the second one, and so on. I'm just going to go in fast motion here. Now, just check a couple of them and see if you're happy with them. Yes, yes, I checked them, they're right. Okay, good. Now, we're going to do our probability distribution now. Okay, now we've just got to rattle off all the possible values of x, which again is 0, 1, 2, or 3. And we've got to sum all the instances of the particular value of x of interest to get their combined probability. So when x is 0, there's only 1 up there, isn't there? Yeah, that's the top one. That's 0.125. I'll just put an arrow on it to show you. So that gets you a 0.125. When x is 1, 2, 3 instances of that. So that'll get you a 0.375 combined probability. When x is 2, you'll get 3 instances, which gets you a 0.375. And when x is 3, that's the very last entry there, you'll get a 0.125. Now, hopefully they will add up to 1. Hope so. Oh, yes, they do. Excellent. Tick for us. So that gets us. Question A is done and dusted. Okay? We've done it, guys. That's it. Right, question B, for you and me. What is the probability that 1 or more heads shows? Well, it's nasty because we're thinking tails. But look, we can think around this question, can't we? What I like to do when they say 1 or more of something, I work out the probability that none of it occurs, and then I subtract that from 1. That's a really good way to go. So what does it mean if we have no heads? That means 3 tails, doesn't it? So that's, if you look at the table to the left, that's a 0.125, isn't it? Yeah, so therefore we want the probability of everything else which would be 0.875. So I've worked it out there, everything else, yeah. So that's when x is 0, when x is 1, and when x is 2, that all adds up to 0.875, Mr. Box. Thank you, Mr. Box. Now, we're really sailing along here, guys. So let's do C for you and me. Let's see how we go with that. Over the page. Good. Now, let's just put our table in there again, and we'll go for number C. The probability that more than one head shows. Look, I'm going to write that out, and then I'm going to convert it to tail thinking. Okay, so more than one head means we want 2 or 3. Now let's just convert that into tails. So that means 1 tail or no tails. Now that's easy to do now. That's 0.375 for 1 and 0.125 for none. And that gets, that gets us 0.5. It does, 0.5. Thank you, Mr. Box. Isn't that great? So we've done it, haven't we? So, how do you feel? Do you feel like you're getting it? I think so. I think you are. And it's really very simple, this stuff. You've just got to make sure that those probabilities add up to 1. If they don't, you're in trouble. You've got to re-look at it, okay? And then everything's very, very doable. So yes, you can do it, and yes, you're a star. So thank you so much for listening to this, and next time we're going to look at measures of centre and measures of spread of discrete random distributions, which is very logical, very interesting, and very doable. Okay? Thanks a lot, and we'll see you next time. Bye.